Hello, thanks for tuning in. Today's unit, we will be talking about pulmonary physiology. Just getting my PowerPoint pulled up here. Look at that, you get a visual as well of the lungs kind of doing their thing. So let's go ahead and get right into it. So again, to kind of review what you would have learned in Anatomy and Physiology 1, we'll look at the anatomy associated with the pulmonic system, sometimes also called the respiratory system. Again, we're going to bring air in through the nasal passageways in the mouth. It'll move down through the pharynx, pass by the larynx, and the epiglottis into the trachea, which will break off into bronchial tubes. So we have a primary right and primary left bronchial tube, or bronchus, into smaller bronchioles, and then eventually will terminate with the alveoli, which we know is the most terminal unit of the lungs, and we know that that's the site of gas exchange. So again, when we think about alveoli and what their job is, essentially they are going to serve as the location for exchange of gases. So again, the blood will pick up oxygen there. The blood will also drop off CO2 there so that we can breathe that out and get rid of that. So again, the alveolar tissue receives the largest blood supply of any of the body's organs. And that makes sense if you think about its function. Again, the cardiovascular system can't do its job if it doesn't have the appropriate amount of oxygen in it and if it can't get rid of the waste products. So again, it's important for us to appreciate that the cardiovascular system and the pulmonary system need to work really closely together in order to achieve both of their general functions. Okay. So we also have this thing called surfactant within the alveoli, and the job of surfactant is to decrease the surface area. So surfactant basically allows the alveoli to stay inflated and can do that with great ease. When we think about the training effect on our pulmonic system or on the alveoli, in reality, again, when I'm talking about training, I'm talking about exercise training. In reality, this system really isn't affected very much, which is extremely rare when we compare it to pretty much every other system of the body would have positive adaptations associated with exercise training. However, what that tells us is this system isn't really a limiter for us during maximal exercise, so it doesn't really need to change, okay? So training effect associated with alveoli pulmonic system is pretty minimal, as I mentioned. However, we can increase the amount of blood supply that we have to this area, so we can increase the capillary density leading to those alveoli, and that would assist us with potentially more pickup of oxygen and more removal of waste products. But in reality, there's not really much change associated with the alveoli. So here you can see I'm just gonna get my notes here. Thought I was missing a page. So here you can see, again, some more things related to the anatomy of the pulmonic system. So again, parietal pleura is going to be the most outer layer. Parietal, again, think parent, so it's going to be the most superficial of the layers. It's a connective tissue layer that's going to help protect the lungs. Then inside of that, we see the visceral pleura. So again, imagine visceral pleura is kind of internal, and then outside of that lies the parietal pleura. Okay, between those two connective tissue layers, notice that we have the pleural cavity, and that will include some serous fluid so that we can prevent the friction of the lungs against any type of other surface. So it's going to prevent abrasion as our lungs inflate and deflate. Okay. Other important things to note in this particular image, we have this interpleural pressure, which is -4. So we have this negative pressure here, which basically allows us to keep the lungs inflated, right? So imagine the suctioning power that's going to allow us to keep those lungs inflated. This is super important. If I lose this kind of suctioning power, then I could collapse a lung. So it's very important that we maintain this kind of suctioning capacity in order for us to keep those lungs inflated. Again, here you can kind of see the relationship between the capillary density and the alveoli. And again, I just want you to appreciate how many blood vessels are going to interact with each individual alveoli, which again is our kind of our terminal unit of the lungs. And that's important because we have to remember what the primary goal of the respiratory or the pulmonary system is, and that's to deliver oxygen and get rid of waste. And the system does a very nice job. It does a great job of allowing us to do those things. And so again, it's just kind of cool to appreciate the density of the cardiovascular system as it's kind of intertwined with the pulmonary system. Okay. Some things that we will cover in lab. Again, this kind of shows you some different components associated with lung volume. I'm not going to give you too much detail because I know you need to define these within your lab homework. But total lung capacity basically looks at how much air can I hold within my lungs. Vital capacity is like the biggest breath I can take in and blowing out the most air that I possibly can blow out, okay? And even when I blow out the most air that I possibly can blow out, there's still gonna be some air left in my lungs, and that's known as residual volume, okay? So we have to maintain just a little bit of air within the lungs, even with our maximal exhalation for that residual volume. And again, the reason that we need to maintain this, number one, it protects us so that we still have some good air left if we were to come in contact with like some dangerous sort of substance that we might inhale. And number two, it helps us to maintain that suctioning capacity so that the lungs don't collapse. Okay. Other components that are pretty important, tidal volume, again, that's just how much air you breathe in and out during a normal breath. Okay. And then I will leave inspiratory reserve, inspiratory capacity, functional residual capacity, and expiratory reserve volume for you to discover as you work on your lab. Okay. Again, another important term for us to note is minute ventilation. And minute ventilation, you can kind of compare this to the equivalent of cardiac output within the cardiovascular system. Okay. So minute ventilation basically just tells us how much air we're bringing in 1 minute, okay? So again, breathing frequency, how many breaths am I taking in a minute? About 12 is about normal for that. And then tidal volume, how much air am I bringing in one individual breath? Again, about 500 mils is pretty normal for that. So multiplying those together, I believe that gives us 6,000 liters of air per minute, okay? Alveolar ventilation, however, accounts for something known as the anatomical dead space, okay? And so what we're gonna look at here is breathing frequency. So again, the number of breaths that I'm taking in per minute times tidal volume, which again we said was about 500, minus dead space, or the air that's not available for exchange, okay? So with one single breath, this accounts for about 1/7 of total alveolar air available for exchange, okay? So again, it takes me about 7 breaths in order to completely replace what I have in the lungs. So almost a minute, 45 seconds, something like that. Okay, so when we think about ventilation and lung mechanics, the lungs are passive elastic structures and their volume depends on 2 major factors. Number 1 is something known as transpulmonary pressure, and number 2 is the stretchability of the lungs. Okay, the stretchability or the elasticness of our lungs will vary depending on mostly just age and like what you do normally, if that makes sense. So smoking will Smoking, COPD will decrease elasticity or stretchability of the lungs. But I mean, for most of us, the stretchability is good, okay? So stretchability of lungs, and then number one was the transpulmonary pressure. We'll talk more about what that is here coming up. So let's take a look at what's the difference between transpulmonary pressure and something known as transmural pressure, okay? And so basically what we're looking at here, so the difference between the pressure inside the lungs and outside of the lungs is known as the transpulmonary pressure, the pressure across a wall. So this governs the static properties of a lung, and it's calculated by the pressure inside of the structure minus the pressure outside of the structure, okay? So again, that's what transpulmonary pressure is, the difference between the pressure inside the lungs and the pressure outside of the lungs. And again, if you remember back to Anatomy and Physiology 1, we know that pressure is a very important component when we try to understand movement within this particular system. Okay, so gases will move via a pressure gradient. So understanding this transpulmonary pressure is pretty important for us to kind of establish in order for us to understand how air will move. Transmural pressure is the pressure that must oppose the elastic recoil in order for the lungs to expand. Okay, so again, imagine that your lungs are these like stretchy structures, and every time I inhale, I stretch out the lungs in order to get the air in, because remember, I have to modify the pressure in order to cause air to flow in down its pressure gradient. So inhale, I stretch out those structures, and transpulmonary pressure must oppose that elastic recoil in order for us to allow the lungs to expand against those elastic fibers. Okay. Determinants of lung compliance. Lung compliance is basically the degree of ease associated with lung expansion. Okay, so how easy is it for me to open up the lungs? Okay, so again, if we think about what the word compliance means, compliance is basically like following the directions, right? Or doing what we're supposed to do. So determining lung compliance gives us information about how easy it is for the lungs to do their job, right? So again, what's the resistance that the lungs must overcome in order to expand, okay? And there are really four components associated with lung compliance or determining lung compliance. Number one is transpulmonary pressure, stretchability, surface tension, and something known as lateral traction, okay? So it's directly proportionate to transpulmonary pressure. So again, the greater the pressure gradient, the easier or the greater the lung compliance is. Okay, so the greater the difference between pressure inside the lungs and outside of the lungs, the easier it is for the lungs to expand. Okay, stretchability, again, would have to do with the health of your elastic fibers within the lung. Okay. Surface tension has to do with surfactant, which we mentioned previously. So surfactant, again, its job is to decrease the surface tension within the alveoli. If I have enough surfactant and I'm able to decrease that surface tension, that's going to allow the lungs to expand with greater ease or increase the lung compliance. Okay. Lastly, this concept of lateral traction. So alveoli and bronchioles are interconnected. The expansion of the lung stretches the alveoli, and as the connective tissue pulls outward, this decreases the resistance. So again, I want you to imagine lateral traction is like blowing up a balloon. Okay, so when I first start blowing up the balloon, it's like hard, right? It's hard to get it going. But as that balloon expands larger and larger, it gets easier for us to blow air into that. And that's essentially what lateral traction is. Okay, so as the lungs expand and stretch those alveoli, so imagine the alveoli is equivalent to the balloon in this analogy, the connective tissue pulls outward and that decreases the resistance. Okay, so as I stretch that balloon out, that allows it to decrease the resistance in the same way that we would see with the alveoli. As I start to breathe in and the connective tissue stretches out, that allows those individual alveoli to decrease their resistance in order for us to bring air in or improve compliance. Okay. Two other I think kind of cool terms, again, I'm a nerd, this is one of my favorite units, is the physiological dead space and anatomical dead space, okay? So physiological dead space is the air that reaches the alveoli, but is not perfused by blood, okay? So let's see. Ventilation without perfusion, okay? So I brought air in to this particular location. The air's ready for exchange. However, no blood comes to this location, so there's no bus to pick up the oxygen that was ready to go at the bus stop here in the alveoli. Okay. Anatomical dead space is air that's in the conduction tubes that's not available for exchange, okay? So again, I bring air in, and we understand that we need to have air basically in all these locations in order for the lungs to maintain their expandability. So again, I'm gonna have some air that's still stuck in these tubes that's not at a bus stop, basically. It's not available for exchange because it's not at the bus stop ready to be picked up by a bus. Okay, so anatomical dead space is the air in the conduction tubes that's not available for exchange. This accounts for about 150 mils. So we have about 30% of the air that we bring in that does not participate in gas exchange, whether that's physiological dead space or if that is anatomical dead space. Again, the difference is physiological dead space is available for exchange, so it makes it to the alveoli, but no blood comes to meet it. And anatomical dead space is air that's stuck in the conduction tubes and isn't available for exchange. It's not at the site of gas exchange. It's not located inside of an alveoli. So this, I love this. So now I want to look at something known as the VQ ratio, or ventilation perfusion ratio, okay? Basically, this represents the efficiency of exchange of gas from the lungs to the pulmonary capillaries, okay? So this involves how well we do at being able to match how much air we bring in with how much blood flow that goes to the alveoli or that goes to the lungs to pick up that blood, okay? So what does this mean, right? So at rest, I'm going to give you the numbers and then explain to you what that means. So at rest, we have ventilation of about 4.2 liters. Again, we took out the dead space, okay? So we're accounting for air that's not available for exchange, okay? So at rest, ventilation is 4.2 liters and cardiac output is about 5 liters, okay? So if I divide 4.2 by 5, that gives me a VQ ratio of about 8.8. Okay, so 0.84. Okay. So basically what that tells us is that we are delivering more blood than the amount of oxygen that we bring in. Okay, so again, is that okay? Is it okay that we are delivering more blood than the oxygen that we're bringing in? And the answer is yes. At rest, we're comfortable. We're getting enough oxygen delivered to the muscles and to the tissues and to the different organs. So we're good to go. That's fine. Okay, so during submaximal exercise, I'm able to increase both variables. I'm able to increase the amount of air that I'm bringing in. I'm also able to increase the amount of blood flow as well. And when I'm during submaximal exercise, I'm pretty darn good at this. Okay, so I'm going to see a substantial increase in ventilation and a modest increase in cardiac output. And so my VQ ratio is about 1.0. And that tells us that this is our most efficient representation of gas exchange, okay? So we're doing a perfect job during submaximal exercise. We're bringing in the right amount of oxygen, we're sending in the appropriate amount of blood to the lungs so that we can pick that up and life is good, okay? So again, 1.0 is our VQ ratio during submaximal exercise, okay? During maximal exercise, again, both variables will increase. We'll see an increase again in ventilation and also an increase in cardiac output. However, ventilation at this point is increasing to a greater extent than cardiac output. So our VQ ratio might be something like 1.2 or something along those lines. Okay, so again, I'm able to bring in more oxygen or more air in comparison to the blood that can come and meet it. Okay, so what does this tell us during maximal exercise? Well, it tells us a couple things. Okay, again, I want you to think about the difference of the functions associated with the pulmonary system in comparison to the cardiovascular system, right? Remember, the pulmonary system, this is his only job. This is all he's got to do. He's got to get air in there and get the waste products out. That's it. That's pretty much all, right? The cardiovascular system has to do a shit ton of stuff during exercise, particularly during maximal exercise. We got to worry about getting rid of heat. We got to worry about coming to the lungs to pick up oxygen, get rid of waste products. We got to deliver those things to a bunch of different muscles and things like that. So there's a lot more demand for the cardiovascular system, right? There's a lot more things to do. He has a lot more tasks to achieve in comparison to that of the pulmonary system, right? So again, it makes sense that the pulmonary system is able to do more than that of the cardiovascular system, right? So what this tells us during maximal exercise is that ventilation and the pulmonary system, as long as we're a healthy individual, is not limiting us, right? It's the cardiovascular system and our ability to get blood to the lungs and pick up that oxygen that's limiting us during maximal exercise, right? And also kind of makes sense then that the modifications that we make when we do chronic exercise are going to be primarily to the cardiovascular system, right? We're going to try to improve the system that limits us from being able to do a lot. So that's pretty cool, I think, to think about those things. So again, I'm going to kind of draw you probably a pretty shitty chart, but I'm going to do my best to draw you a chart to kind of show you the relationship between ventilation and perfusion during each of these 3 time points. Okay, so imagine this is rest. I know I'm slow and it's not super great, but we'll do the best we can. Here's submaximal. Hey, where'd my S go? Maximal. Okay, so rest, submaximal, maximal exercise. That's what we're looking at here. Okay, so again, let's start with that's ventilation. Okay, let's see if I can change my color to do ink color. Heck yes, I can. All right. So ventilation is in red. See, now I wish I would have been smarter. I could have done the cardiovascular in red. Next time. Let's see how I do here. And this is Q. Okay, we did pretty good there. That was okay, I'm decent. So again, at rest, see that cardiac output. Let me get my laser back. Cardiac output is greater than ventilation. And again, that gives me a VQ ratio about 0.8, okay? Again, I'm bringing in less oxygen than blood flow, but that's all good because we don't really need that much oxygen when we're not doing anything. Okay, submaximal exercise, we see these two cross over. So now my ventilation and my blood flow are equivalent. So the most efficient that I could potentially be is here during submaximal exercise. During maximal exercise, again, notice both variables have continued to increase. Ventilation increases to a greater extent in comparison to cardiac output. Again, when we think about their functions, their jobs, we understand that cardiac output is a limiter for us. However, The pulmonary system, not a limiter for us, okay? So again, at this level, our VQ ratio is probably 1.2, something along those lines. And again, this tells us that ventilation is greater than cardiac output during this particular scenario. Okay. So next thing we want to look at is gas exchange and transport. Again, as we've kind of already alluded to, we know that gas exchange is really based on this idea of pressure, right? So we've got these different pressure gradients that we need to understand in order for us to understand movement of gases. Okay. Additionally, we need to understand what's going on with gas concentration as well, because we know that concentration and pressure will be interrelated, okay? So ambient air, or the air surrounding us, we're talking about environmental air when I say ambient air, always contains the same gas concentrations, okay? So it doesn't matter if you're in Iowa, if you're in Colorado, if you're in the desert, wherever you are, the concentrations of the gases should remain the same, okay? Oxygen concentration is about 20.93%. CO2 concentration is 0.03%, so very, very little there. And then the majority of our air is made up of nitrogen. So 79% of the air is made up of nitrogen, okay? So the ambient total pressure varies depending on altitude, okay? So again, a lot of people think at altitude there's less oxygen, when in reality, the concentration, the percentage stays the same no matter where I am. So the percentage is 20.93%. However, the total pressure decreases as I move to altitude. So let's take a look at what that looks like. Okay, so here you can see changes in total barometric pressure, or sometimes it's called total partial pressure, as I move to altitude. So again, at sea level, you can see that my partial pressure is about 760 millimeters of mercury. If I move to Denver, that's like about 500 or so millimeters of mercury. Pikes Peak, you're getting close to, I believe it's like 418 or something along those lines. And then again, notice like Mount Everest, the total partial pressure is around 200. Okay, so again, as I move up in altitude, the total pressure decreases. However, if I'm at sea level, Denver, Pikes Peak, or Mount Everest, the percentage of oxygen is still 20.93%. Okay. So let's take a look at how this then applies to the partial pressure of a singular gas, okay? So Dalton's law tells us that each gas exerts its own partial pressure, okay? So the total partial pressure of the atmosphere is the sum of all the partial pressures, okay? So again, we said that as we move up in altitude, the total pressure will decrease. So here you can see the difference between, now I gotta change my color back. Here you can see the difference between sea level, which we said was about 760 millimeters of mercury, in comparison to altitude, about 420 millimeters of mercury, okay? So in order for me to figure out what the partial pressure is of an individual gas, I need to take the total pressure times the percentage of that particular gas that we have, okay? So in order to figure out what oxygen is, I'm gonna take 760, I shouldn't have tried to write this. 760 times 0.2, that's a 2. And that gives us a partial pressure of oxygen of 159. Okay. In order for, I'm not going to write these out, but you should write them down. In order for me to figure out the partial pressure of CO2, I'm going to take 760 times 0.0, what was it? I already forgot. 0.003. Okay, so a very small amount, and that gives me a partial pressure of 0.2 for the CO2. And then for nitrogen, I'm going to take 760 times that its partial pressure was 0.79. So if I take 760 times 0.79, that gives me a partial pressure of about 600. Okay. So again, if I add up those partial pressures, that gives me the total pressure of 760. So 159, about 1 for CO2, and then 600 for nitrogen gives us a grand total of 760 for the total pressure. Okay. Now we can understand how, when we modify the total pressure, how each individual partial pressure will also decrease. Now, I don't really care about nitrogen. That's not going to be that important when we look at gas exchange. However, I do very much care about what happens to the oxygen partial pressure. Okay, so at altitude, as I take 420 times the 0.2, or about 20%, that gives me a partial pressure of about 88. Oh, come on, get out of there. Yeah, this whole doing it with your mouse is like pretty tough. I'm not gonna lie. 88, okay? Again, so we can understand why people think there's less concentration or there's less oxygen when we're at altitude. In reality, the partial pressure is decreased, but the concentration stays the same. Okay. Again, I don't care if you know what the partial pressures are for PCO2 and the partial pressure in nitrogen at altitude. Again, just appreciate that they're less than what we would see at sea level because the total pressure has decreased. Okay. So again, as we have alluded to previously, in order for us to facilitate gas exchange, we need to have a pressure gradient in order for this to work. Okay. So again, I want to kind of take a look-see at the numbers associated with what's happening at sea level, and then we can understand why it's problematic for us when we're at altitude. Okay. So as air enters the trachea, again, let's remember that we're starting with an ambient partial pressure of 159. Oops, sorry, that goes down here. 159. Okay. As I bring air in to the lungs or into the trachea, the air will become saturated with something known as water vapor. Okay. And water vapor is equivalent to 47 millimeters of mercury. And basically what it's going to do is it dilutes and humidifies the air as it comes in. Okay. So the pressure, this water vapor pressure, the humidifying capacity associated with water vapor, allows us to decrease the partial pressure to 149. Okay. Alveolar partial pressure decreases to 105 because it's mixing with air that's already there. Okay, so again, it mixes with both the physiological and anatomical dead space. Again, we know that with each individual breath, I'm not getting rid of everything and I'm not bringing in 100% new. We're only replacing about 1/7 of what we have in each individual breath. Okay, so alveolar partial pressure will decrease down to 105. Okay. Then we look at what's going on in the capillaries and we see we have a partial pressure here of about 100. So important things to note. Partial pressure decreases as we move through each of these structures. That is essential in order for us to establish a pressure gradient so that oxygen can move with ease, okay? Now, remember, when I'm at altitude and the ambient pressure is 88, well, shit, that screws up the whole system, right? If I don't establish that gradient here, it becomes really difficult for me to get the air in and do the things that I want to do with oxygen, which is why altitude can become so threatening for us or become a physiological challenge for us because it takes away these pressure gradients. Okay, so again, now I want to take a look at Henry's law. And Henry's law basically tells us that gas can dissolve in a fluid in direct proportion to the pressure of the gas in its gaseous environment. Okay, so on the previous slide, you saw that the alveolar partial pressure was about 105, and the partial pressure within the capillaries, pulmonary capillaries was 100. Okay, so with Henry's law, basically it's saying like, oh, I can jump from my gaseous form into the water, no problem. Okay, so I'm able to transfer gases from a gaseous form, such as in the alveoli, to into the bloodstream pretty easily. Okay, two factors that affect how well we do with this, or how much gas diffusion can occur into the liquid. Right, number one is going to be a pressure gradient. Okay, so again, if I have a high pressure gradient, that increases the likelihood of the gas then dissolving into the fluid. And then second is the solubility of the gas. Okay, and solubility of the gas basically tells us how comfortable does the gas feel moving into the fluid. Okay, so I will give you an example of this. So my husband and I are both swimmers. Well, we both do like triathlons and stuff like that. And I'm totally a baby about cold water. Okay, so we get to the pool and we're gonna, do our laps, do our workout, and we both get there and we get like, I get my swim cap on and I like sit on the edge of the pool and I like dip my feet in, and then I dip my goggles in and get my goggles cleaned off and like splash a little bit of water on my face so the goggles are gonna stick there, and then make sure my watch is ready and it's set on the setting to go swim and everything, and then like I'm slowly easing myself into the pool. Like it's like a 10-minute process. If the water's cold, it's like a 10-minute ordeal for me to get in the water. Okay. My husband, on the other hand, he throws on his swim cap, throws on his goggles, and freaking does a cannonball into the water like every time, and splashes me and thinks it's like the most hilarious thing. Right. So the ease of movement into the water is significantly different from one to the next. Right. So I am equivalent to oxygen. Okay. Oxygen's solubility to a fluid is not very high. Okay, so it's harder for oxygen to move into that fluid in comparison to CO2. CO2 is my husband. Okay, he just freaking goes. He just jumps right in. He doesn't care if it's cold. He just goes for it. Okay, so the solubility of CO2 is 20 times greater than what we see of oxygen. Okay, so CO2 can move really easily from one form to the other. It can move from its gaseous form into the water, and then it can move equally as fast from the water back to its gaseous form. Whereas oxygen's a little more timid. Like I got to get myself warmed up. I got to get my mindset right in order for me to like get in the water. Okay, so that's what we're talking about when we say the solubility of the gas within the fluid. Okay, so let's take a look at all like what all is going on in order for us to deliver oxygen. Right? So I'm going to start on this side, on the oxygen side, the PO2. You can see, again, we've already kind of filled in most of these. So we know ambient partial pressure was 159. We said within the trachea, it was 149 as we added that water vapor pressure. Okay, within the alveoli, we said it was about 105. And then within the the blood leaving the capillaries is about 100. Okay, so again, those are all factors that we have already filled in a previous chart. The only one left to fill in is what's going on in the systemic veins. Okay, again, if you remember back to the cardiovascular system from a previous time in your life, you'll remember that the veins' job is to carry deoxygenated blood. Okay, again, we're not using all the oxygen that we have. However, we are going to use a significant amount. Okay, so systemic veins will have about 40 millimeters of mercury for its partial pressure of oxygen. Okay, so again, now you know all these numbers. 159. Let me get my pointer so you can, I don't know if you can see the little pin marks. So ambient 159, tracheal 149, alveolar 105, systemic veins 40, and capillaries 100. Okay. Now let's take a look at P CO2. Okay, ambient is about 0.2 millimeters of mercury, tracheal and lungs about 0.2, alveoli is about 40, systemic veins is about 45, and blood leaving the alveolar capillaries is 40 again. So notice that these three variables are pretty darn close, and that's completely fine because that solubility that we discussed in the previous slide is so high that that's no problem at all. Okay, notice the difference we saw here, right? The systemic veins only had 40 for their concentration or their partial pressure in comparison to the alveoli, which had 105. Okay, so again, that pressure difference is significantly greater with oxygen, and it needs to be because the solubility is less in comparison to what we see in the carbon dioxide. Okay, so when we think about diffusion of oxygen from the alveoli into the capillaries, again, we see a small amount of mismatch from 105 to 100 usually. And again, this is going to be due to two factors. Again, this tells us that there's some level of inefficiency. It's not perfect, but it's pretty darn good. Okay, so we have something known as venous admixture, and this is when some of the blood dumps directly into the venous system. Okay, so we have some blood that's not going to the lungs to pick up new oxygen. Then we also have something known as physiological shunts, and this is when some blood goes to the alveoli to pick up oxygen, but the alveoli is not perfused with that particular alveoli is not perfused with oxygen. Okay, so the bus comes to the bus stop, but there is no oxygen there to be picked up. Okay, when we think about gas transfers in tissues, during exercise, oxygen consumption increases and CO2 production also increases. So how does this affect PO2, CO2 levels? Well, we would understand then that as we use more oxygen, right, the venous PO2 is going to be less than 40, and also we're going to produce more waste products. So the venous PCO2 might be greater than 45, might be like 50, 55, 60, something along those lines. Okay, so again, as we see these modifications within the tissue, we can understand how a greater pressure gradient might be established and help us to move more in an exercise setting. Here you can see what's going on as it relates to internal respiration and external respiration. Okay, external respiration, again, is the movement of gases from alveoli into the blood and from the blood into the alveoli, whereas internal respiration is the movement of the gases from in the blood to the tissue and from the tissue back into the blood. Okay, so here you can see normal skeletal partial pressure of oxygen is about 40, right here. And partial pressure of CO2 is like 45. The pressure difference between the gas in the blood and the intracellular level must create a pressure gradient. Okay, so again, we know that as I start to do more work in this particular area, I'm going to decrease PO2 because I'm using more of it, and I'm going to increase PCO2 because I'm producing more waste. And so that's going to establish a greater gradient for us. This is one of the most important factors in determining how much diffusion will occur at the level of internal respiration is something known as diffusible distance. Okay, so how far from the capillaries is that tissue? How far does that gas molecule have to travel physically in order for us to then be able to use it? Okay, the less the diffusible distance, the greater I am at exchange. The further the diffusible distance, the worse I am at being able to exchange this. Okay, and that's a factor that we can modify with training. We can increase the capillary density in a particular tissue, and that's going to allow us to have a lower or a smaller diffusible distance, which is good for us as it relates to quick transfer of gases. So next thing I want to focus on is what's happening. How do we transfer these molecules? How do we carry them, right? So blood can carry oxygen in two different forms. We can carry this as dissolved in the blood plasma, and this is going to account for a very small amount of oxygen. And then also it can carry oxygen that is bound to hemoglobin. And this will account for the majority of oxygen carried. So two other concepts to understand when we think about the movement of oxygen within the blood. One concept known as cooperative binding. Okay, so basically with cooperative binding, there are 4 different hemoglobin molecules within one red blood cell. So imagine that this is a car with 4 different seats. Okay, my example for this is a little bit weird, but maybe it'll stick for you. Have you ever, like, you go to the airport and there's like a shuttle that will take you to your hotel or whatever after when you land? Okay, so you get to the airport and you land and everything, you get your bags and you go get in that shuttle. And the shuttle will never take just one person, right? It'll sit there and wait until all the seats are full, basically. Again, why are they doing that? Because it's more efficient. It's more efficient for that driver to take like a bus load or a full car of people via that shuttle in comparison to just if it just ran one person back and forth, right? And that's basically what cooperative binding is. Okay, so cooperative binding, we've got 4 seats on the red blood cell. And once I bind one oxygen molecule to one seat, the affinity for these other seats increases substantially. Okay, the affinity means like the attraction of oxygen for those particular seats will increase substantially so that those seats get filled up so that this red blood cell is super efficient and it's carrying like, a full load of oxygen versus not being efficient and not carrying much at all. Instead of carrying just one, we want it to be fully like at capacity. Okay. Yep. So cooperative binding, the binding of one molecule of oxygen increases the affinity at the 3 other binding sites. Okay. So again, that's what cooperative binding is. Hemoglobin saturation tells us the number of hemoglobin binding sites in comparison to the total binding sites available. Okay, so again, let's say that I've got 100. I'm going to make the math really hard here. I've got 100 red blood cells, so each one has 4 seats, so I have 400 available binding sites. Okay, and let's say I have 300 of them filled. Okay, so if I have 300 of them filled divided by the 400 total that are available, my hemoglobin saturation is 75%. Okay, so it's the number of hemoglobin binding sites that are bound in comparison to the total number of binding sites available. Okay. Normal hemoglobin saturation is like 98% within our arteries. So we're really good at getting oxygen onto these red blood cells. Okay. This is, I think, a little confusing to a lot of people, but this just shows us something known as the oxyhemoglobin dissociation curve. So this shows us the relationship between hemoglobin saturation and our oxygen partial pressure. Okay, so again, at the level of the arteries, of the pulmonary arteries, the partial pressure is about 100 for oxygen, and notice that the saturation of hemoglobin is close to 100%. It's like 98% is normal, okay? However, as I move to the veins, for example, notice that the partial pressure will decrease. Again, we said the partial pressure of oxygen within the veins is about 40, and that brings our binding or hemoglobin saturation down to like 70 something, okay? So again, we still have 70% oxygen saturation in our deoxygenated blood. So that's kind of crazy to think about. Okay. Other factors can shift this curve in either direction. Okay, so I can shift the curve to the right, and that's good during exercise. I can do that by modifying some of these variables. If I increase temperature, if I increase waste product, if I increase this product known as 2,3-DPG, which is like a byproduct of metabolism, and if I decrease pH, all of those factors will cause me to have a decrease in affinity of oxygen, which basically means that I'm better at being able to drop off the oxygen at the level of the tissue. the oxygen wants to jump out of the blood and get to the tissues is basically what happens here. So this is a good thing. That's a positive thing here. That's called the Bohr effect, B-O-H-R. Bohr effect is when I shift that curve to the right, and that will enhance unloading of oxygen at the tissue level. Okay, carbon monoxide, again, this is kind of a application type of slide. Carbon monoxide, again, you've probably heard of it. You've got carbon monoxide detectors in your house, I would think. And basically, carbon monoxide is a colorless, odorless gas, so you wouldn't like smell it or see it or anything else like that. But basically, it can take the seat of oxygen on the hemoglobin molecule. So it has a significantly higher affinity for hemoglobin, 210 times greater than that of oxygen, okay? So basically, if you were exposed to carbon monoxide, it would take the seat of oxygen on those hemoglobin molecules because the affinity is so much greater. And this is going to reduce oxygen binding, and it will eventually lead to death because I'm not able to bind the oxygen molecules. Even though the oxygen molecules might be available and they're just fine, but because the affinity for hemoglobin and carbon monoxide is so much greater, then the carbon monoxide will take the seat of oxygen on that hemoglobin charter bus or whatever. Okay. Nitric oxide is another molecule to consider when we think about gas exchange. Nitric oxide can bind with hemoglobin, so it's like the equivalent of oxygen carrying like its little suitcase. Think of it that way if we're going back to our airport example, okay? So I can ride that bus. Again, there's 4 seats on the red blood cell, and I can bind nitric oxide right alongside of oxygen. Okay, so again, imagine nitric oxide is like my suitcase. Okay, nitric oxide can be produced in the peripheral tissue, and it acts as a vasodilator. So it's a positive thing for us to have. Nitric oxide can enhance our ability to deliver oxygen because it acts as a vasodilator. So it helps us to get more blood to tissue and that sort of thing. Okay. Okay, AVO2 difference, or arteriovenous oxygen difference is the long term for it. AVO2 difference, artery vein oxygen difference. Tells us the difference in oxygen content in the veins in comparison to the arteries. And basically, what does this information give us? Well, it tells us how much oxygen we have extracted at the level of the tissue. Okay, so how much were we able to get out of the blood and deliver to that particular tissue? How does the AVO2 difference change during exercise? Well, it needs to increase because I'm going to keep the artery level the same, but I'm going to decrease the amount in the veins, which tells us that I'm delivering more oxygen at the tissue level. Okay. What other factors might affect AVO2 difference? Again, probably how much I have in the arteries, how much I have in the veins, and then also what type of work am I doing within that tissue, and what's the diffusible distance as well. So all those factors would be important for us in determining AVO2 difference. Okay. CO2, again, 3 ways for us to transport CO2. Again, this is slightly more complicated than what we saw with oxygen. We can have some CO2 that's dissolved in plasma, and that accounts for about 5% of our CO2 transportation. Number 2, we can have some CO2 that is bound to red blood cells, and this accounts for about 15% of our CO2 transport, and this will form carbamino compounds. So when a CO2 molecule binds to hemoglobin, it's known as a carbamino compound. Okay, and then lastly, about 80% of our CO2 will be transferred in the form of plasma bicarbonate. Okay, so again, that accounts for 80%. Okay, so here you can see kind of those 3 different options. So here you can see dissolved CO2, which we said was a little bit like 5%. Here you can see CO2 bound to hemoglobin through that carbamino compound. And again, we said that was like 15%. And then we can convert CO2 into HCO3, which is bicarbonate. Okay, but really it produces a bicarbonate molecule and an H molecule. Okay, this H molecule is acidic. This bicarbonate molecule is basic in nature. Okay, so those are kind of like your three different options for the CO2. Okay. Oh, one other thing to note. So then when I get to like, so this is what happens. So I produce CO2 like in the tissues or whatever, and then I'm ready to carry the CO2 to the lungs to get rid of it. So some will be dissolved, some will bind to hemoglobin, and some will form bicarbonate. Okay, so they'll carry this to the lungs, and then they're all converted back into CO2, and then we breathe out CO2 in order to get that out of our system. Okay. All right, respiratory quotient, also known as RER, RQ, or sometimes just straight up R. This basically looks at or allows us to compare how much CO2 I've produced in comparison to how much oxygen I've consumed. And the information that this gives us is it tells us information about what is our fuel source that we are using in order to get energy. So that's kind of cool, the combination of, looking at the pulmonary system and how it is interrelated with the metabolism, really. So that's pretty neat. Again, values for RQ or the RER ratio range from like 0.7 to like 1.2, something along those lines. But it'll basically give us information about if I'm burning fat or if I'm burning carbohydrates. And again, those of you that are Loris students that are within the kinesiology major, we'll talk in a lot greater detail about this in exercise physiology. We'll get the opportunity to test this in each of you in that class as well. So that's coming if you're interested in the relationship between like fuel use and the respiratory system. Okay. So how is the respiratory system regulated? Again, it's fairly complex. But the medulla will serve as kind of our location for that baseline. And this will allow us to adjust the rate and depth of breathing to meet metabolic needs. We also have chemoreceptors, which are located in the aortic arch and carotid arteries. And these chemoreceptors are going to be sensitive to changes in oxygen, CO2, and many other things as well, but they're most sensitive to the changes in CO2. Okay, so again, as CO2 levels increase, then they will send a signal up to the medulla to say, hey, we need to increase the rate and depth of breathing so that we can get rid of this waste product. Also, a decrease in oxygen would stimulate those feelings as well. Okay. Again, some voluntary control of breathing as well. So again, we can try to control breathing when we're doing activities such as swinging, singing, swallowing, speaking, swimming, weightlifting. Those are some examples of complex activities where we try to manipulate and control breathing via voluntary control. Okay, if the CO2 levels are too high though, breathing will take place involuntarily. Okay, so like your body will take over and be like, no, we got to freaking breathe right now, as opposed to like letting you try to control your breath. Okay, changes in ventilation. So again, exercise causes an increase in ventilation. 3 mechanisms associated with monitoring changes in ventilation. Sorry, I don't have a slide, or I don't have notes for this one. Changes in ventilation, 3 mechanisms responsible for changing ventilation. I'm sorry. 3 mechanisms I would say would be proprioceptors. So again, body position changes, your body would notice those. Also, there's some level of like higher order thinking. So again, the frontal cortex will give us information that's like from higher order that we're like, hey, we're going to be exercising. So like, here's what to do. You know what I mean? And then lastly would be feedback from the chemoreceptors. Okay. A couple last things to note as we kind of move here forward. But when we think about non-steady state exercise, we have this concept of ventilatory threshold. Again, this is highly related to something that we'll spend some time talking about, anaerobic threshold or lactate threshold. All of these factors are, I don't want to say they're the same, but they are basically the same. And basically, ventilatory threshold is the point at which pulmonary ventilation increases disproportionately with oxygen levels. And this will occur as a result of the lactate threshold or as a result of excess lactate production. And this represents the interaction between anaerobic and aerobic metabolic systems. And like I said, it'll occur concurrently with either anaerobic threshold or lactate threshold again. So those things are interrelated. Again, as I start to produce more waste or lactic acid, I'm going to increase breathing, not because I'm trying to get more oxygen in, but because I'm trying to get rid of the waste products, that CO2. So I'm trying to get rid of those waste products in that particular scenario. Okay, so here you can see the relationship between ventilatory threshold and lactate threshold. Again, with training, ideally, I should be able to do more work before I start to have that kind of buildup of lactate and therefore increase ventilation as well. Okay. We think of energy costs associated with breathing. How much am I spending calorically to complete that breathing process? Again, remember it's going to involve the intercostals, the diaphragm, pec minor, sternocleidomastoid, could involve abdominal muscles if I'm breathing forcefully as well. So again, trying to understand what's going on from an energy standpoint. Light exercise and at rest, we're spending about 3 to 5% of total oxygen consumption. During moderate exercise, 8 to 11%, and during maximal exercise, it's accounting for about 15% of our energy expenditure. Okay, a couple things to note about acid-base balance. Again, this is one of the functions or one of the primary goals of the pulmonary system is to help us maintain acid-base balance within a narrow window. So when we have alkalosis, this is when we see a decrease in blood acidity or an increase in pH and a decrease in hydrogen. Okay, so there's not enough acidic molecules in the blood. Acidosis is the opposite. So we have an increase in H or increase in acidic molecules, and that causes a drop or a decrease in pH. So what does the respiratory system control, or how does the respiratory system work in order to help us modify the acid-base balance? Again, probably has to do primarily with breathing rate. So again, can I get rid of CO2 quickly or more quickly or less quickly in this particular scenario? So again, I want to breathe more if I'm in acidosis. I want to breathe less if I'm in alkalosis. Okay. So an increase in CO2 production, again, causes an increase in H, which increases the acidity or decreases pH. H can be buffered by bicarbonate to prevent changes in blood pH. So again, bicarbonate is basic, H is acidic. So if I have both of those, they like cancel each other out. Okay. 4 different, I guess, scenarios here to think about when we think about acidosis versus alkalosis. Okay, so metabolic acidosis results because I am accumulating a lot of H molecules, so I'm doing a lot of work from a metabolic standpoint, and the kidneys will play a role in compensating for this. Okay, respiratory acidosis results from not breathing effectively. So let's say I am swimming and I'm trying to not take a breath or whatever, I could experience respiratory acidosis as I start to build up those waste products, but I'm not breathing in order to kind of take care of that. Okay. Metabolic alkalosis is the result from a decrease in H molecules in the blood. This causes a decrease in respiration and, like we said, retention of hydrogen molecules so that we can increase the acidity. And respiratory alkalosis is the result of hyperventilation. Okay, the kidneys can compensate for this by excreting bicarbonate or getting rid of that basic molecule that we have. Again, respiratory alkalosis is something that we would experience, like if we go to altitude, that's kind of like a pretty common issue for us to have. And again, the reason for that is the body's trying to compensate for that change in pressure. Okay. Hypoxia is a deficiency of oxygen at the tissue level. And so there are 4 different classifications or 4 different types of hypoxia as it relates to the pulmonary system. So hypoxic hypoxia is also known as hypoxemia. And this is when the arterial oxygen levels are decreased. Okay, so I have less oxygen in the arteries for some reason. Okay. Anemic hypoxia is when oxygen is available, but I don't have enough red blood cells available for binding that oxygen. Okay, so the lungs are doing a good job, but the blood is lacking in red blood cells, so therefore I can't carry enough oxygen. Okay. Ischemic hypoxia is when blood flow to tissues is too low. Okay, so again, maybe I have enough oxygen coming in and I have enough oxygen in the blood. However, there's a blockage for some reason that's preventing blood to flow to a particular area. Okay. And then lastly, histotoxic hypoxia is when oxygen is available, but the tissue is unable to use the oxygen for some reason, probably related to the cell's metabolic machinery being altered. Okay. That is it for the pulmonary system or the respiratory system. Again, if you have any questions, please let me know.